If you have any objections, let me know. Now, so let me actually give you some references. Now, there is an online book called deeplearningbook.org. You could look at it. There are a lot of chapters there. You can just get started with that. And there's a shorter book. This is also online. Neural networks and deeplearning.com. And I actually started reading this, and right away you can get to practice some code. So that's the nice thing about the second website. Now, there are two ways in which we can, as a group, use the above books. If you find the above books exciting and accessible in terms of the mathematics it uses, just dive right in, and we can talk about it on this forum. If mathematics is not your forte, you could still benefit from this if you could just look at a lot of these aspects as black boxes. You could just download the code from GitHub, just run it, tinker with it, and the code is in Python, and it's a very easy language to follow. The setup is also easy. I hope to actually run this code in the next session. Well, so that's the plan. So let's go into some more details. Now, supervised learning is the machine learning task of inferring a procedure or inferring a function from labeled training data. Now, when you say training data, it consists of training examples, and each example is a pair. You can look at it as a pair consisting of an object, which is, you can think of that as an input object, and typically a vector, and a desired output value. So at the outset, you are given a set of examples where you have input data and then the desired output. Supervised learning is a way of training your model to arrive at a function. Well, basically, your model is the function. So you'll run your procedure to arrive at a function that'll that'll infer the function that actually maps training data to the examples. And also, if it can also work on labels that it has not seen so far, on test data that it has not seen so far, and it extends that functionality in a reasonable way. Now, that's what supervised learning is. Now, unsupervised learning is different. You don't have examples. It's just that you have data and you're supposed to find patterns in data that's eventually useful for your analysis. Reinforced learning is done by two things. The first step is to explore, try some paths, and see what the results are. And based on the results, you basically keep that. The results inside your calculations for the next explorations. For example, you can have a neural network train itself to play chess. So it can have two programs playing against each other, and then find out the best moves as it proceeds. This is one kind of reinforcement learning. So what we are going to see today is the Hello World program of machine learning. That's what it's called. It's called the digits recognizer problem. You can see this on kaggle.com and various other places. So the problem is to model a classifier that can train to do the following. To get at a classifier that using a set of bitmap images of handwritten numerical digits and their associated labels as input, it can train itself to identify any handwritten digit. So as you can see, one of the applications of this would be identification of zip codes that you may write on packages that you send out. So that's one, sent out by mail, the snail mail, I mean. That's one application. Another application is, if you have noticed, at the ATM machines, you can actually deposit a check, and you can, the machine will identify and ask you whether it provides you a number and asks you to confirm that that's the number you wrote on the check. So this again is one of the applications, and they're pretty good at doing identifying handwritten digits. Now, this is what you see on these ABM machines is probably more sophisticated than what we're going to see here today. Now, this would be the problem. Given a 28 by 28 bitmap image of a handwritten digit, recognize the digit, and that is classified to belong to one of the following labels. And the way the way this is done is by training your model, and once it's trained, it can actually perform this task. Now there seems to be several algorithms available. KNearest Neighbor algorithm is one of them. What KNN does is the following. It uses the training set and creates a layout of all the training points in a multidimensional space. And the number of dimensions of that space will be equal to the number of elements in the vector. In this example, for example, you have 28 by 28 bitmap image. You can see that as 28 times 28, which is 784. 784 grayscale pixels, and they correspond to 784 numbers, where each number goes from 0 to 255. Right. So that's a vector, and the number of dimensions you have for that is 784. Now, so what this does is it lays out the training sets. So if you look at one picture or one bitmap image, you can think of that as one point in this 784 dimensional space. Now for the training sets, if you have n items in your training sets, you're looking at n points in that kind of space. What the deep learning algorithm, what KNN algorithm does in this case is this. Now, it just lays out those points in that space, and when you provide that with an image that it needs to identify, it places that in that same space and then looks at K neighbors, K nearest neighbors. Now, out of the K nearest neighbors, if a particular images associated with a particular digit has as the maximum, proximity to this point, that means more of those that particular digit are neighbors to your point than the others, then that will be elected as your result. So that's the idea of KNN. Now, deep learning algorithms, it looks like they're much better. While KNN can get 90% right, deep learning algorithms seem to get more than 95 or 98% in some cases. They get that many right. So what we'll discuss today is is multinomial logistic classifier. So this is just a precursor to the definition of a neural network that will do this. So we'll just go with just this model, and in the next session, I plan to actually show you the code that runs this. Now, a logistic classifier basically does something like this. So given your input vector, which is x, in the case of the digit recognizer, your x basically is the 784 pixel image, which is 784 numbers ranging from 784 integers ranging from 1 to 255, 0 to 255. Now that's x, and this is called a bias term. So what we are going to do is, you have examples. You have a number of these x's and you have a number of these y's, which are the results of this, which are from the training set. And we set up an equation like this. This is a matrix. If you have, let us, in this case, we have 10 classes. That means the vector here should be 10 dimensions. Well, and then you can think of this as a 10 by 784 matrix times x, plus this is a 10 by 1 matrix, which is just basically a column vector of 10 dimensions. So inferring weights and biases, that means arriving at W and B. That's the idea of this, by using many examples of X and Y. Now, so this is how it goes. So you basically have Wx plus B equal to Y, and let's say that that's the vector you get. And we apply something called a softmax function, which is defined by this. S of xi is, this is just the number E, which is which is what you see. Well, the exponential, right? It's I guess you know what that is. So e raised to xi by sum of e raised to xi. This is what we are trying to get at. So what this does is it makes sure the number that you get eventually here, they look like probabilities. So if you add up these, you're going to get 1. So you apply a softmax function and get that. And well, these are some properties of softmax function. Let's ignore that for now. So the scheme goes like this. You start with X. You have a number of Y's. So you start with an assumption of some W and B, and then calculate this and see if it is close to this. And over a number of iterations, you'll basically fine-tune the values of W and B. That's the idea. Now, in order to see how you actually go from one iterations to the other, you have to have a way of finding how much off you are from the result. So you start with a vector, and let's say you got something like this, and if you have 3 classification, your first item can look like 1 0 0, the second will look like 0 1 0, and the third will look like 0 0 1. And let us say this is the number you got, and you have to have a notion of a distance between what you got and what actually this is. And one way of setting up a distance function is known as cross entropy. And cross entropy is defined like this. Now I have to tell you that there are other ways of setting up your distance functions. The simplest thing is the mean square distance, which is you basically take the difference of these numbers for each one of them, and then you square them, add them up, take the square root. Which is basically, it look like how you do the distance between 2 points in 3-dimensional space, in this case. Now that's one way of doing it, and it looks like this cross entropy gives you faster convergence. That's why people use cross entropy these days. Well, this is definition of entropy. I'll skip this. I think we'll you can just look at look at some literature on this. So this basic entropy basically means average information per message that flows over a channel. The concept of entropy comes from information theory, and it looks like well, cross entropy is derived from this concept, and it looks like a natural fit for this training. Now, as I said, the most common error function is the mean square. So this is how it's defined, and it looks like cross entropy is preferable over mean square error. So to summarize, the scheme is something like this. You have an input vector. You have a set of input vectors. So in this case, let's say you got one input vector. This is just one of them, and you calculate wx plus b for an assumed set of values w and b. You arrive at this, and you apply softmax, get something like this, and look at cross entropy between the actual value that it should have got and this, So that gives you a sense of distance, and that will tell you how much off you are from your result. So this is step number one. Now, once you know how much off you are, you should be able to take some measures to close in on the actual results. So the idea is to tweak these numbers based on this distance that you see, not per example. You need to look at the whole picture of all these errors across your training set in some way, and then start tweaking these numbers. So for that, you need to actually define something more. So we define what's known as a loss function. So which is basically, you look at the cross entropies. So if you look at it, S is basically the softmax on WXI plus B. The subscript I here is the ith element in your training set, and I actually runs from 1 to n. This is assuming that you have n numbers, n examples in your training set. Now what this is giving you is the average of your errors. That means, you're looking at these distances, which actually indicate how much off you are on an example, and you're summing this over all examples, which means, you're looking at how much off you are in total, and divide by n gives you an average of how much off you are. And optimizing this function is what training is about. That means you're supposed to, you need to get at values of W and B for which this is minimum. That means the error is minimum. So that's the idea. Now, how do we do that? Now, it turns out that, well, before we get there, we can look at what's the complexity involved. Now, if you look at W is in this case, you have a 10 by 784 matrix. That means you have 784 times 10, that many unknowns. And B is a 10 by 1 matrix, so you have 10 more unknowns. So that means the parameters that you are trying to assess, is 7,850. That's a lot, actually. So that is for one example, and you're looking at n such examples. Your n in the digit recognizer set, you have 60,000 examples. So you have 7,850 times 16. That many. Well, it's not that many parameters, like you're trying to estimate these, and then, if you look at this, you're looking at that many calculations. So your loss function itself is a huge calculation, So, and that's what computers are good at these days, and nowadays, for large matrix calculations, GPUs are used. CPUs, it looks like they're slow. GPUs seem to speed them up. And it looks like GPUs came from gaming technology. And it's proving to be very useful in calculating such large matrix operations. So the way it works is this. So you'll start at some point, calculate the loss function. This is assuming that instead of 7,850, if you have just two parameters, 1 and 2, weight 1 and weight 2, this is how it looked like in 2 dimensions. I mean, this is actually 3-dimensional again. So you calculate the loss function, and then you look at the gradient. So gradient is actually the direction in which the function changes most. So that gives you, so if you look at this as a three-dimensional surface, that is the path of steepest climb actually. Gradient actually goes that way. If let us say the minimum is here and then you're climbing up as you go, the gradient vector will be pointing away from the minimum. So you take the negative of that, multiply it with some small alpha, and then get to the next point here. And you do the same thing, get to the next point there. You do this iteration after iteration. Each iteration is called an epoch. And so after some time, you should see that you'll reach a point where you don't have a way of improving your estimate. So you'll reach somewhere here, and so that's the idea. And so this is what gradient descent is. Now, stochastic gradient descent is done because of the by stochastic. That it is. You can imagine that it's a sample that you're looking at. Since you have many examples here, so what you do is you take a random sample out of that, apply it on a random sample. The reason is loss function itself is huge, as you saw. It's a lot of calculations, and calculating the gradient is roughly 3 times. It needs roughly 3 times the resource, and then you have to do this over many iterations. So one way to shortcut this is to actually calculate the loss function on a random subset of the training set, and then arrive at an optimal optimization of this. So this basically is how it's done. Now that's what this is. So in the next session, I plan to cover the following. How you'd actually implement a logistic classifier using a neural network. Basically, how do you turn that into a neural network? So we look at the definition of neural networks, and like like what is it that you can do on top of this to make that a neural network, and hopefully I'll be able to cover backpropagation, which is actually the implementation of the gradient descent, I believe. So I need to check that out. And then an implementation of neural networks. In fact, I actually have a program that does this. Let me take a couple of minutes to show you this. I haven't gone into the details of the code, but I can show you this. In order to do this, I need to start up my Linux machine. So well, I'll wait a couple of minutes. It's while it starts, we can just look at this. Now, this book that I mentioned here, this has a link to a GitHub repository. It has Python code that implements neural networks for this program. So you can go to that website, look for this link. I think it's in the chapter 1 of this book. You can download that, and you can, I think before you run it, you will need to install a couple of things. Like you will need to get the basic Python interpreter. You will need Python 2.7, not Python 3.4 or 3.5. So Python 2.7, NumPy, SciPy, and you'll also need scikit-learn library and a library called Theano, Theano. So these are the things you need to install on your VM. So once you have that, you'll be able to run this program. So let me show you how I ran that. It looks like, well, from the output, it looks like, it gets 95% of the validation results right. Okay, so I mean, running this is as simple as this. I just put those comments in the text file here. So I need to start up Python interpreter. Well, you could just package this into a Python script and run it at once, but this is just to show you, how we could do it. This is as simple as this. You can go to the GitHub repository, install the set of libraries. It has a README file that'll tell you what you need to install before running this. Just get the code and okay, so this is what the first line did here is we took the data in one of the folders and well, it basically imported the Python module that will actually read the data. So I think that the next one is what's going to read the data. So load data wrapper, this function is implemented in this Python module. And it reads the data and it breaks that into 3 sets of data. And the training data, which is the set of examples. And validation data is also, it's actually a piece that's broken from this. So training data in this data set has 60,000 examples. So what this author has done is this: out of the 60,000 examples, he has separated about 10,000 of them and made it validation data. So the reason is, if you have training data, you train your model based on that, you can run it on validation data, and then check how well the training went. And this validation data has 10,000 examples. And the next step would be to run it on test data and then look at the results. So this is the neural network implementation in his code. So it sets up a neural network of 3 layers. The first layer has 784 input nodes. The second layer has 30. The third layer has 10. You know, I mean, if you're interested, you can just look at why these numbers are so. I'm going through that as well. So at this time, I don't know why it's broken down into this. I understand. You know, that's the number of that's the size of every input vector. Why 30 as hidden layer and why one more layer here? And looks like this SGD is stochastic gradient descent. So this is the one that actually trains the model. So it runs for a while, about, I'd say about 5 minutes or so. So while it runs, you know, in every epoch, it says, you know, in the first epoch, that's the first iteration of identifying the loss function. I mean, of identifying the optimal values. It gets 82% right. As you can see, you know, it's actually improving with every iteration. So while it runs, you know, we can just review the plan. You know, as a group, you know, I would suggest, you know, you can go look at the code if you want to just look at the code, or if you want to get deeper into the definition of neural networks, you can do that as well. I suggest that you go to these 2 books, and then if you have something interesting, you know, we can just talk about that in our next meetups. So yeah, I mean, it's basically just to reiterate like the slide. You know, if you like the math part of it, you get him, you get that algorithms. If you like to just tinker with the code, you can get the associated code. The code, as I said, you know, it's here. If you go to that link on one of the pages, you can see a link to GitHub repository. You can download the code and practice. Now, again, you know, our big picture again is this. We'd like to talk about big data stack and you know, machine learning algorithms, and then NoSQL databases. Anything about data analytics at scale. So that's the idea. Well, actually, that's all I have. You know, if you have any questions or suggestions, please let me know. You know, you can unmute your session, and then so this is how this is going. You know, it seems to get 94% right. So the next thing I want to do is to actually feed the image of one of them and see how it works. So I haven't done that yet. So maybe I'll have something, and then view the image and see how it's getting split, or take a random sample of about 100 images, feed those images into this network, and visually inspect if it got all of them right. You know, so it looks like it stabilizes around this. You know, it's going to go around, you know, 28 or 29 iterations, and you see actually it actually dropped. So it gets about 95% right. So it looks like you know, there are improvements that can be done to this, And one of the things we could aspire to learn is to look at the increments on this and to learn more about neural networks. So this is just about neural networks. You know, I also am quite excited about these technologies as well, and I hope you are too. So if you have anything on these, yeah, please talk about that. Okay, that's all I have for today. So I'd like your feedback as well. You know, if you can unmute and let me know what you think. I see something on the chat. Yeah. Okay. Swapnil, are you there? Okay.
Yes,
Okay.
Kumar.
Yes. Swapnil, your question is, what's the practical use of the program I just created? I mean, actually, as I said, you know, this program is just downloaded. I didn't create that. You can get at the program on that link that I showed you. Well, let me actually put that up again. So, I mean, you can download that code and practice also. No, that's the link. Now, what's the practical use? You know, like if you, you know, image recognition is a very complex problem. Like one of the, for this particular digit recognizer problem, you know, the application is this. As I said at the beginning, the immediate application has been in post offices and bank ATMs. If you write a check with numbers filled in at the right spot and feed the check to the machine, you know, the machine identifies the number that you have written on the check. And even if it's a handwritten, you know, you can read the handwritten image, break that into pieces, and you get at the classification of each digit, and that's how it does that. So this, it's already there, and you know, this program is actually it's supposed to be the hello world program of machine learning, and so you can actually look at the code, you know, to see how things are done. I think Gulse has a question. Like, does that answer your question, Swapna?
Yeah, I got that.
Yeah. Well, in fact, Google uses this a lot. I think, you know, the Street View application of Google, right? You can give a picture. You can take your own picture of some street and then give it to Google. Google will tell you the address of that location.
Right.
Right. So so that is actually, you know, one of these. That's a much more complex neural network that they use there, I believe. In fact, the head of Google's deep learning department is actually a professor from Toronto University, and it looks like, you know, he had a startup and then Google bought the startup, and it looks like, and he has been at the forefront of this research. You know, Jeffrey Hinton, you know, if you'd like to look up. Well, Gursev has a question, so what's the email ID in case you need to get? Gursev, you're looking for my email ID, right? Let me type that here. Okay, kvenkat2006@yahoo.com. So that's mine. Do you have any questions now, good sir? I mean, you can unmute, I mean, or if you don't have microphone handy, you can type. Okay, thanks. Okay, what I'll do is, if you could, go to this poll and let me know your preferences. This is for a physical meetup. We'll continue to do the virtual meetups. So if you go to the Big Data Analytics meetup page, look at this tab, more, and then polls. So there's a poll here. If you could just indicate your choice, that would be great. I guess a couple of you did that now. Yeah. So this is a nice feature. So it looks like Sunday morning is more popular. So yeah, I can arrange for a meetup. So one of the things that I'm looking at is, there is a cafe in Mississauga at Tompkin and Eglinton area. It looks like they offer free space, so you can go there, and use that space. It's free as long as the event is free for participants. So that's all I have. Thanks for coming.
Hey Kumar, this is Ganesh here.
Hey Ganesh.
I have one question. Is this the image reading is something what it is currently implemented in the CAPTCHA? Do you know when they put the image and ask us to enter the number and they will validate with the CAPTCHA image, right?
CAPTCHA probably not. I mean, that's different, I think.
Okay.
CAPTCHA again, it already knows what that is, and then that is different. So I mean, actually, let me actually spend some time on that. Like, if you go to Kaggle, Kaggle.com, if you look at, you go click the tab competitions. Actually, they have competitions that are real competitions, and they also have things that are for learning.
Okay.
I think. Okay. Okay. So do you see this digit recognizer?
Yeah.
This is the problem that I just talked about. So if you look at it, you'll get a description of what the problem is. You'll also get training data and test data. And this MNIST data, MNIST stands for Modified National Standards Institute data, I believe. So this data is well, analyzing this is like the Hello World program of machine learning. So.
Okay, I'll take a look.
Yeah, you can take a look at this.
Thank you.
Okay. So I have. Thanks everyone. Thanks for joining.